All right, so here's the electron microscope itself, and there's really three parts to it. There's what's called the column, which is where we generate a beam of very high energy electrons. There's a sample chamber in the middle, which is where obviously you load the sample. And then the bottom part is basically a pumping system and electronics control unit. So the way the microscope operates is we have up at the top of the column, we apply a very high voltage on the order of anywhere from 5,000 to 30,000 volts to eject electrons from what's called a field emitter tip. And this beam of electrons that's ejected from the tip is focused through a series of electromagnetic lenses down into the sample chamber. The sample chamber is kept at a very low pressure, around 10 to the minus 6 torr, and the column is at a pressure of around 10 to the minus 11 torr in order to avoid the electrons interacting with air or other bad things happening to the electron source. Then the bottom part here is basically the pumping system that has the electronics in it. So the way the microscope works is we have this beam of electrons that get focused onto the sample, in principle to a diameter of about 1 nanometer. So basically those electrons are focused onto one single point on the sample. When those electrons come in and hit the sample, it's like a rock hitting water. It generates a big splash, and those splashes are called secondary electrons, and those secondary electrons go off to the side, and we detect those using these detectors. There's 3 different kinds of secondary electron detectors on this microscope. Also, every once in a while, an electron will bounce straight backwards, and we can detect that using a backscattered electron detector, which is basically in the column itself. So the reason for having multiple kinds of detectors is there are many different contrast mechanisms in electron microscopy. Sometimes we want contrast based on the atomic number, and so heavy elements are very good at scattering electrons back where they came from, light elements not so good. So the backscattered electron detector tends to be more sensitive to seeing heavy elements. The detectors that are off to the side essentially generate what looks like a topographic contrast. There's shadowing effects that occur when the electron beam comes down and we measure the electrons that get kicked off to the side. So you get an image that has a little bit of a three-dimensional view to it. So the way the image is made is that beam of electrons is focused down to a single point on the sample, but now it's raster scanned back and forth in this direction and back and forth in that direction to basically scan over some period of time of anywhere from a second to 10 seconds to raster scan over the sample of interest. At each point, as that electron beam is raster scanning across the surface of the sample, we measure the electrons that are being kicked off, and we represent that electron signal as an image. So the more electrons that are kicked off at a given point, we represent that as white, and if there are no electrons being kicked off, we represent that as black. And you'll see what those images look like in a few minutes. In addition, in this particular instrument, we have a regular video camera. The video camera is located in the back of the electron microscope. You can't see it, but what it does is it will show us the sample on a larger distance scale, and it shows us the very end of that column. So this right here is the end of the column in the vacuum chamber, and it's where the electrons are emitted from. And then we'll put the sample, you'll see we'll raise the sample up to a certain position below that, below the electron gun. And then the detectors are off to the side and you can't see them right now. Okay, so the next thing that we're going to do is open up the sample chamber and see how we put the samples in, and you get a little view of the inside. All right, now we're going to open up the chamber. It's been vented to atmospheric pressure. Okay, so that's opened. I'll zoom up. You can maybe see the sample holder. The little things right there are motors. So the sample is actually mounted on a motorized stage so that you can move it longer distances. And Jamie, my graduate student here, will put the sample holder mounted on there. All right, now we basically close it back up again. And the next step is now to evacuate the chamber and get it ready to image. Okay, now that we have the sample in the chamber and it's been evacuated, Jamie Wheeler, one of my PhD graduate students, will be raising the stage. So if you look on the computer monitor, you'll be able to see that coming up. I'll zoom up in a second here so you can see that better. Alright, so again, now you're looking at the inside of the chamber and you're seeing the top of the electron gun and you're seeing the samples as viewed from the inside of the chamber. Now we're going to switch over, turn on the electron beam, and now you're going to start seeing the image. So right now we're zoomed out pretty far. And as Jamie moves in, you'll be able to see finer and finer detail. There's a lot of focusing that has to go on so that we can see what is see what the sample actually looks like. So we've sort of pre-focused this already to eliminate some of that, but as we zoom up to higher and higher magnification, you'll begin to see that this is a sample of nanowires, and these happen to be zinc oxide nanowires. And I'm going to move the camera so that we're perpendicular to the screen. And now you have a better view of what we're looking at. You see there's a scale bar here. So the scale bar is a 200 nanometer scale bar. So you can see that the nanowires that we're looking at right now are on the order of 20 nanometers in diameter. And right now we're looking at a pretty fast image, so it's almost scanning the image a number of times per second, so it's nice when you're focusing. If we want to get higher resolution images, we can slow down the scanning rate and do a line average or a frame average, and now you see the quality of the images goes up considerably. And we can potentially maybe zoom up even more. We can try this. So the little gizmo in the middle is to help focus the image better. It kind of wobbles back and forth. And once that's done, the image is better quality. And we can go back, and again, instead of looking at it at a video rate, we can slow it down and get higher quality images. And at this point, you can use a scale bar, for example, to measure various dimensions and get accurate measurements of the diameter of the nanowires and other physical properties. Okay, so I mean, that's basically the microscope. So we hope that with your copper oxide nanoparticles and nanowires, we should be able to see them in much the same way as we're looking at these zinc oxide nanowires right now. Okay, this is another instrument that at the very end we will use on a small number of samples in order to determine the chemical composition of the samples using a method known as X-ray photoelectron spectroscopy, or XPS. The idea of XPS is to send in a monochromatic beam of X-rays onto the sample, and that will eject electrons from various core levels. So things like carbon 1s, copper 3d, copper 2p, and those electrons that get ejected will come flying out, and we will measure their kinetic energy. And by energy difference, h nu, which was the energy of the photon, minus the kinetic energy of the electron after it comes out, tells us how strongly those electrons were bound within the material. And those binding energies are very characteristic of the elements, and then also undergo smaller changes that are a reflection of the oxidation state of that particular element. So within the system, we have an X-ray generator. So the X-ray generator is located right down here. So it generates electrons from an aluminum material, and those X-rays have an energy of about 1490 electron volts. Those X-rays travel up here to what is an X-ray monochromator. So the X-ray monochromator has a large quartz crystal mounted up here. It's about that big in size. And that sends the X-rays down into the center of the chamber. This particular chamber is, again, at a very low pressure. The pressure is about 1 times 10 to the minus 9 torr on the inside of the chamber, and the sample would be sitting in the center of the chamber. Most of the stuff that you see over here is facilities for introducing a sample from air into the very low pressure region of the chamber. And then over here, this somewhat curved object is an electron energy analyzer. So there's a lens that sticks into the sample chamber. The electrons come flying out. This is an electron lens, and then we can measure the kinetic energy of the electrons using this lens over here. Most of the rest of the system is for pumping out the system and for moving samples around and for doing various kinds of manipulation of the sample. We can also, instead of using X-rays, one can use ultraviolet photons, and that turns out to be useful for looking at what's called the valence electron structure. So things like the HOMO orbitals, the highest occupied molecular orbitals of a solid, are usually referred to as the valence band. It's where the valence electrons lie. And so we can also characterize that using a lower energy excitation source. For the purposes of this project, what we'll do is we'll use this monochromatic beam of monochromatic beam of X-rays, pick out the electrons, and from that we'll be able to look at the chemical composition of the sample and determine whether the copper is in the +1 or +2 oxidation state, and also determine quantitatively the ratio between copper and oxygen. Okay, so here's the kind of data we get from the XPS. We can operate it in a survey mode, as I've shown here, in which case we essentially get a map of the entire elemental composition of the sample. So in this one spectrum, we see a whole bunch of different lines, each of which corresponds to electrons being emitted with different kinetic energies. We translate that kinetic energy into a binding energy. And the relative intensities of the various peaks tell us something about the relative composition of the sample. So we know, for example, that carbon is at 285 electron volts. It's a relatively weak peak. In this case, we have some silver on the sample. That gives rise to peaks around 370 eV, oxygen in this neighborhood, and other elements as well. Once we determine what elements, we can zoom in into specific regions. So if we look, for example, at the carbon region, we can do what's called a multiplex spectrum. And here we look in detail at one particular element. And the important thing here is that different elements, for a given element, if we have it present in more than one oxidation state, we will get more than one peak. So in the case of carbon, for example, neutral carbon will hold on to its electrons with some intensity and therefore will give rise to electrons at a particular binding energy. If that carbon is oxidized in the form of a carbonyl group or a carboxylic acid, it will hold on to its electrons more tightly and it will increase the binding energy. So here we have a binding energy of 284 volts, and here we have a binding energy of 286 volts. So using that, we can determine what's the distribution of oxidation states within an element. Perhaps more importantly, by quantitatively determining the area under these peaks, we can determine the ratios of different elements. So that was carbon, here's oxygen. Again, we see multiple different forms of oxygen. Here's silicon, which is the main material in the sample. And so the interesting thing about XPS is it gives us not only the distribution of elements and their oxidation states, but allows us to quantitatively determine how much of each element we have in the sample, and from that determine the actual stoichiometry in a non-destructive way. So in the design projects, we'll be able to use this to show whether the copper is in the copper 0, copper 1, or copper 2 oxidation state from the energy of the copper peak. And we'll be able to infer the stoichiometry by looking at the ratio of copper to oxygen and integrating the areas under those peaks.